Okay, good morning, everybody. So, I'm going to be talking about Starling Bank and how we built a reliable cloud-based bank in Java. So, I'm going to start up by saying why reliable? Why is reliability in the title? Reliability is going to feature a lot in this talk. Reliability is important because it's probably, if security is concern zero for people who are using banking services for customers of banks, then reliability is concern one. So reliability, the ability to know that payments that you have scheduled, the card that you're using, anything that you've set up in your banking is going to work and is going to take the correct amount of money away from you and give the correct amount of money to the person you want to give money to, that is probably most people's second concern after security when it comes to banking. Making sure that they know where the money is going and that the money is going at around about the correct time. So, we have already heard one horror story about finance and software in Night Capital. Let's listen to another one. So, it is the 18th of June, 2012, and we are at a major high street bank. I'm not going to name which one to spare them their blushes, but a major bank. And some engineers are actually probably their ops team is preparing to release some code. And this code is a change to what's called a batch job scheduler. And this is a thing that basically takes a list of jobs that need to be run overnight and decides in what order they should run and when they should run. So it's not doing anything particularly itself, it's just going run job 1, run job 2, run job 3, etc., etc. Great. So they've got everything in place. They've tested the code. It works in dev. They've made sure that, they've got the appropriate sign-off from the appropriate people. And they make sure that they've got a backup plan in place, a rollback plan, just in case things go wrong. So they know they can roll back. Great. So they've got all of that in place. And they press the button and release the code. The code release goes fine. So now it's out in production. And they sit there monitoring production as the batch job window kicks in and the scheduled jobs start running. And they're not too happy with it. There are one too many errors. Performance isn't as good as they would like. So they're a bit uneasy about having released this code. So it's the next day, the 19th of June. And the engineers and ops people and various other people meet up and they decide, you know what, this hasn't really worked. We're going to initiate the rollback plan. And that is when everything starts to go catastrophically wrong. The rollback plan is initiated. It seems to work fine. The code is taken out. But unbeknownst to them at the time, while they managed to successfully roll back the code, their database changes hadn't rolled back successfully. So now the database and the code were out of sync with one another. So when the batch job started kicking in on the evening of the 19th, the scheduler was making all sorts of bizarre decisions. It was kicking off jobs before other jobs that needed to be run had run. It wasn't waiting for those jobs to finish correctly. It was taking the output of jobs that had produced bad data, bad results, and feeding them in as the input to other jobs. The system started getting more and more out of line. There was just complete chaos. So it gets to the next day, and no one knows has a clue what's going on. Payments that should have been made haven't been made. People's house sales have to be put on hold or fall through because they're not sure if the mortgage has been arranged correctly or not. And even worse, for one subsidiary branch of this bank, the batch job on the 19th hadn't finished by the time the batch job on the 20th started running. And you can imagine what sort of chaos that caused. So we have all of this chaos, all of these payments out of place, people not really sure if they've paid their money correctly, paid twice, not at all. No one really knows what's going on. Customers are angry. How long do you think this took to sort out? Any guesses? We've got a week and 6 months. It's between those two. It's about a month, not quite a month. So it's the 10th of July by the time that people have got everything sorted out and all customers are back to where they should be. Their balances are correct, their payments are correct, and so on. So this is obviously suboptimal. This is what we don't want to be doing. This is a horror story of trying to change code and it going very wrong. And these people weren't changing code at speed. They weren't, deploying microservices to a cloud-based infrastructure or anything like that. These were traditional banking people taking their code and going through a highly regulated, highly manual, eyes-on release process to release to a server that was presumably in the building with them, rather than in a data center somewhere, who knows where. So how did this happen? How did this go so wrong? They had everything in place. They checked the code. They tested the code. They reviewed the code. They got all the appropriate sign-off from all the appropriate people. And it wasn't even as if they were hubristic. They weren't sitting there going, you know what, nothing's going to go wrong. They had a rollback plan in place. And, they used it. So what was wrong? What didn't they do? Well, what I think went wrong with this scenario was that the people involved accepted the possibility that they would fail, but the software didn't. The software, all the software, the batch job scheduler and all the scheduled jobs it was running, thought that everything would be correct, in place, accurate, and ready to go when it started. So the software was naive in thinking that everything would be fine. So this then is, I suppose, the main kernel of my talk, that if you want to build software which you can scale, if you want to build software that can run reliably and rapidly, and develop it rapidly, innovate rapidly, and so on, you have to build software that is mistrustful. So reliable software is mistrustful software. It is software that doesn't take for granted that everything will be in the right place. So I'm now going to go through how we've used this concept of mistrustful software to manage to build a bank quickly and at the same time build it reliably. Who here has heard of Starling Bank before I got up on the stage? Okay, quite a few people. For those who haven't heard of us, we are a fairly new bank, so we've been going for almost a year now. It was almost a year ago that we released into the App Store. We're a 100% mobile bank, so we only exist on your mobile phone. So you apply for a bank account by downloading the app, installing it on your phone. You go through the application process entirely on your phone, and we've got many interesting and innovative features, I think. So all of the traditional features around making regular payments, a debit card and so on, that you would, overdrafts, that you would associate with a standard current account, plus interesting things such as giving you the ability to segregate all of your money into different pots, savings goals, integration with not only Apple Pay and Google Pay, but also Fitbit Pay, and other different payment systems, giving you aggregated spending insight data into where your money's gone, and so on and so on. We're also developing we've got an API, open API that you can go and code against. And we've got a marketplace of various partners who are coming in from the insurance sector or the pension sector who are coding against this API and integrating their app with ours. And we've just launched business accounts as well. That's the other feature we now have. So, how did we build all of this stuff really quickly while at the same time maintaining reliability and wanting to grow our volume and scale our volume, the number of customers we have, as fast as we possibly can? So, start off, a basic background in how we've architected the system. So, we have what are called self-contained systems. So if you go online and look for self-contained systems, you can find this whole software architecture philosophy around them. We don't fully follow that. We don't fully have that as our architecture, but we do use some principles from it. So we have a load of systems on our back end that do various things, and we generally try and contain those systems so that they're doing one thing. It's not exactly microservices, but it's definitely not a monolith. I like to call it a microlith. So, halfway house between the two. So we've got, for example, an application that deals with card payments. So that deals with receiving messages from our card supplier about people trying to, make card payments and then responding back to them. We've got one that deals with connecting to the faster payments network so that when you send money from the app to another bank account, that deals with processing messages from that. We've got another application that deals with holding and maintaining your balance and list of transactions that you've made, for example. So we've got all of these different systems that are isolated, they have their own code, they have their own database, they have their own API that can be used to connect either to the mobile phone or the app on the mobile phone, or it can be used to connect to our internal web browser-based application that we have that allows the managers of the bank to work out what's going on, or to each other, so they can communicate to each other. So we've got all of these different things, and we need to make sure that all of these applications play reliably with each other, that they all manage to communicate, transfer messages between each other and to the phone and to the management system, and to, now that we've got the marketplace out there, connect to our partners and so on, and deliver all these messages in a reliable fashion. Now, here's where we come down to reliability. I'm not going to list all of the possible things that could go wrong with the software, because there's, obviously there could be loads of things that could go wrong, and even if you tried to name them all, you'd fail, because there will be, as Donald Rumsfeld says, unknown unknowns, things that you don't know, things that just come up. But generally speaking, there are a smaller number of ways that you can classify into what happens, what the outcome of things going wrong is. Now, I'm going to avoid talking about one of those things that could go wrong is chaotic emergent events where a system has an unexpected side effect. I'm going to leave that one to one side for now, because that is very difficult to anticipate or plan for. And we find at the moment it doesn't happen that much. So I'm going to classify problems that you can have, or the outcome of those problems rather, as one of two things. Either you try and do something and it doesn't happen, or you try and do something and it happens more than once. So those are basically the two categories of things we're trying to avoid. Someone instructing a payment and the payment going out twice, or the payment not going out at all. So idempotency became a very big concept for us in trying to avoid those two outcomes. Who knows what idempotency means or has heard the term before? No? A few people? Okay, good. Idempotency is the concept that if I run the exact same command more than once, tagged with the same unique identifier, that command will only be run once. So if I go execute command ABC, and then again I say execute command ABC, the command ABC will only actually be executed once. And the second time I ask for it, the system will go, yes, I've already executed that. So that is trying to avoid running the same thing more than once. You can find much more technical definitions of idempotency online on Wikipedia, but that's the definition the practical definition that we use for it. So we invented this brilliant acronym for our architecture, which stands for lots of autonomous services continually trying to do idempotent things to each other, or l'oschiaditio, which sounds like a town in Italy and didn't exactly roll off the tongue. And then we, after some suggestions from Mr. Adrian Cockcroft, who was mentioned earlier, we shortened that down to ditto architecture. Do idempotent things to each other. So, concept of ditto architecture, of all of the different self-contained systems we have running idempotent commands on each other and making sure that they can communicate with each other in an idempotent manner is the core of our architecture and how we make sure we maintain this reliability. So the first rule, the golden rule, is do everything at least once and at most once. Now, some of the brighter ones in the audience might be thinking, well, don't you mean just once? Isn't that what that means? And yes, it sounds like a very fancy way of saying do things just once. But actually, saying this in this expanded format better defines what the architecture is, because those are the two problems you've got to guard against. Making sure that you do things at least once, but you also do them at most once. And the way we have this, the various systems communicate with each other in an asynchronous manner. So we've got to assume the possibility that if we communicate and say, hey, System A says to System B, hey, System B, I'd like you to do this, System A has to anticipate that that might take some time. So it can't just sit there waiting. It has to fire off a command and say, System B, do this, and get back to me when you've done it. So each system is constantly, because of this asynchronous nature, because things might take longer than you're willing to wait, what we are doing is working towards correctness. So we have what we call eventual consistency. And this is an important sacrifice to acknowledge, that maybe things won't be consistent instantly. But we don't need them to be consistent instantly. We need them to be consistent eventually. And we think that the reliability we want to develop and making sure that the services are all eventually reliable within a reasonable amount of time is more important for us and for our customers than having it, instantly there, instantly available. Because we make some gains in being able to sacrifice that instantaneousness in many circumstances. We can't sacrifice it in all circumstances. The main one that we can't sacrifice it in is card payments. When you go up to the card reader and tap your card to pay for something, that needs to be pretty instantaneous. But in most other cases, we can, work towards eventual consistency. The other thing to realize is important to realize is that the systems, there are no distributed transactions across the system. So you have multiple systems executing code, and you have to take into account the fact that one of those systems might fail, but the other ones might succeed. So you might have done half a job, and you have to consider that possibility. You might have correctly run your code over in System A, but not in System B. and you have to be able to catch up from that halfway house position. And then at the bottom, that very important principle I started with, build mistrustful code. Don't trust that the other systems have managed to successfully run something. So let's go through an example here. So this is an example of making a payment. So we have 3 systems involved in this, which are called customer, payment, and bank. Customer is the main gateway for the customers to interact with the back end. So the mobile is connecting to customer, and the mobile registers that the customer has said, I'd like to make a payment, please. Now, what we do here, the first thing we do is we just acknowledge that request, and we give it a UID. So we give it a unique identifier to say, this customer has made this request to pay £20 to someone else. Great. We then have to communicate that to the payment system and say, hey, payment system, this customer has made this request. Great. And then the payment system can communicate back and say, I acknowledge that you have made this request, and I will make it. The payment system then has to put that in, say, great, send that payment message off to the faster payment system, which is an external system, which all the banks connect to make these payments, to instruct the payment there. The payment system then has to make a further call to bank, and bank is the thing that controls the ledger. It's got the ledger in it, it's got the account balances in it. It controls how much money the bank has, how much money the bank owes to faster payments, for example. And that has to be recorded, the fact that we now owe more money to the faster payment system at the end of the day. And payment contacts bank, and bank comes back and goes 202 accepted. So that's the happy green path, the smiley happy path that we all like. What happens if things start going wrong? So the customer contacts through the mobile phone and says, I'd like to make a payment. That is sent to the customer application, which goes, received, I've got your message, thank you very much. Records that command in the system. It then goes, hi, it then goes to the payment system, hi, I'd like to make a payment, please. And the payment system isn't there. It's down for some reason. And so it can't respond, so it just goes, nope, no response, or a bad response. So customer just goes, fair enough, okay. And then it has this retry concept. So it retries that message. It goes, right, wait 5 minutes, try again. Payment, I'd like to make this payment, please. And then let's imagine that payments come back up. And payment then goes, okay, accepted, thank you very much. Great. So now we've made the payment. So we've managed to get this through, and we've fulfilled the at least once concept. So we've managed to instruct that payment by constantly asking, can you make this payment, can you make this payment, can you make this payment? And eventually we get the response back, and we go, great, that's complete. Customer can sign it off and go, I have done this at least once. Payment, let's imagine, then makes the faster payment and then has to contact bank to say, hey, bank, I'd like to register that this money has been paid. So it goes off to bank and says, record that we owe faster payments some money at the end of the day. And bank acknowledges that, records that, but then doesn't send the message back. The message gets lost along the way somewhere. So we've recorded in bank the fact that we need to make this £20 payment, but we haven't managed to contact that back to the payment system. So then payment, obviously, following the retry concept, will retry and say, £20 payment, please. And bank will get that command, it'll look at the UID on that command, and it'll say, well, hang on a minute, I've already processed a command with this unique identifier, so I'm not going to process it again. So it then fulfills the at most once criteria. It then says, no, don't need to do this again. Great, I've already done it. So just go, yeah, accepted. I've already done that for you. That's fine. And then payment will stop asking. So with a combination of this, the constantly retrying until you get accepted, and the checking on the other side to say, well, have I already run a command with this unique identifier? We can fulfill both the at least once and the at most once. So we can make sure we do things, but we can make sure that we do them idempotently. Now, this being a software engineering track, I need to show some code. So I'm going to show you the code which we use to implement this. And it's actually quite simple. There are only two interfaces that we need, or an interface and an abstract class that we need to implement this. So the first one is called recoverable command. Recoverable command is an instruction. It says, what do I need to do, and how do I record that I have done it? Those are the two questions it asks. So, all right, what do I need to do? I need to instruct the payment system to make this payment. How do I record that I've done it? Normally by time-stamping a record in the database to say, this one has been done. Thank you very much. And there's the code. That's the interface in its entirety. Read that very fast, because I'll go on to the next one. Catchup processor. Catchup processor is the second part of this architecture. And catchup processor is the thing that does the retry. It says, what data items should I attempt to reprocess, and what command should I use to reprocess them? So obviously, what command, it's linked to a recoverable command. Every catchup processor links to a recoverable command and uses that command to run things. And what data items should I attempt to reprocess? It basically looks over things that don't have that timestamp, that haven't been recorded as completed done. And it runs, say, every 5 minutes or every minute, depending on how quickly you need it, and it will pick up a load of items and then reprocess them. Again, here's the abstract class bit. Now, what benefits does that give us? I'll go through these quickly. The benefits that gives us, of having constructed the system with this architecture in mind, with this mistrustful code, there are quite a few of them. The first is that instance termination becomes safe. It's safe to take down an instance of a server, or even multiple instances of a server, or even all instances of a server. Because if you've taken them all down, and it turns out there's a problem, it turns out it was doing something, it's fine, it'll catch up. It'll catch up and do everything in an asynchronous manner, but it will do those things. It'll catch up later and rerun the code through the catch-up processes. So you can kill it for whatever reason. You can kill it because you're doubtful about its security, or it's not really started up, or just because you want to test things. We have a chaos engine running in production, killing servers, taking them down just to see how we'll respond, which is pretty nifty for a bank to do. You can deliver quickly as well. This means that you can take code that you've written and quickly deliver it into the back end. Because if something goes wrong, as long as you've followed these principles, then any errors that you cause, any mistakes that you cause, can be quickly fixed, the code deployed, and then all of the commands that have built up going, I can't run, I can't run, I can't run, will filter through the system. And it might take a little longer for them to filter through, but they will filter through. We will have this eventual consistency. Now, because of that, we have managed to turn the traditional banking IT on its head. So most banking IT has this very, slow sign-off process where you have to wait for months and months and months to get sign-off, and then a huge batch of code gets released into production after having, hundreds of eyeballs on it. And the place where the banks can do the more innovation is at the front, where the customer's eyeballs are, and they can iterate slightly faster. But the back end, the server code, is still quite slow. We go the other way around. So we deploy code to production, at least once a day, sometimes twice, 3, 4 times a day. So we can deploy that server code in the safe knowledge that we're not going to remove anybody's payments and that we can catch back up to where we are in a reasonable amount of time within the same day if something has gone wrong. And we tend to release app releases weekly or fortnightly. And if something goes wrong, we have a load of metrics. We have a load of graphs up on the screen that show us exceptions being thrown. And we get this traditional pattern here. We have most of our applications have 2 instances running in production. So what you can see here is the customer server reporting a problem. And you can see there every minute, I think that is, there are 2 spikes where an error happens or 2 errors happen. So things are going wrong. Customer is constantly retrying every minute to do these things. Each server's retrying every minute. And it's got this constant yellow spiky pattern. And that will be quickly picked up because it's on a graph on a wall, on a screen shown to the whole office somewhere. Someone will pick that up, look at it, say, oh, that's the problem, code a fix, release a fix the same day, and then watch those spikes go away. So it's easy to release fast and maintain reliability. Quick question on why Java. Some of you might be asking that. Java is good for this because exceptions are noisy in Java. They don't get squashed. They squawk loudly. You can see them in the logs. You can report them on the graphs. So because that, you've got that loud, squawky nature of Java, it means that it's easier to see when things are going wrong. And because it's easier to see when things are going wrong, you can get people on it faster and get them to fix it faster. And the system can go, well, there was an exception thrown there, so I'm going to retry that later. So everyone knows that things are going wrong. It's also easier to integrate with legacy third parties. There's a large job market for it. Other things that help us bring that reliability. So finally, I'll wrap up with some important takeaways. First thing, give everything a UID. If you want to implement this sort of architecture, you have to give everything you do a UID, whether it's a command, an instruction, an object, a person, a payment, a transaction, everything has a UID. And because everything has a UID, you can easily identify whether you've done it before. So you're not sitting there going, well, the customer did make a payment with the same amount at around the same time, so are those the same thing or not? No, you're going entirely on the unique identifier. Everything gets, as soon as it enters the system, it gets assigned a unique identifier. And then we can know what we've processed about it fairly easily. It's not just hardware that can fail. It's not just people that can fail. Software can fail. Your software can fail. It will fail. And you have to not just you assume that the software can fail. You must make your software assume that it can fail or other pieces of software it's integrating with can fail. Cherish your bad data. Don't get rid of it. Don't eliminate it. If you've got a demo system full of cruddy data that has been built up over the years by people coding, half-coding things or making mistakes or what have you, brilliant. Use it. Use that bad data because that bad data can be used to show the resilience of your system, show how it responds in different circumstances, show whether it is reliable or not. And finally, you can do anything you can undo. So if you are able to undo it, then within a reasonable amount of time, then you are able to do it. And that gives immense freedom to people to be able to release things quickly and make sure that everything innovate constantly and keep going, keep developing, keep expanding, keep scaling, and so on. And if you've got this architecture in the background, these principles that ensure reliability, then you can do that. So that's my talk. Please check out our developer website if you're interested with integrating with the Starling Bank API, and check out the Starling Developer Podcast. where we I host that, and we go through various different aspects of building the bank quickly, how we achieve this reliability, security, and very many other topics. So that can be found wherever you get your podcasts from. Thank you very much.